Hi, my name is Prabhanjan, and I'm going to talk about pre-constrained encryption. This is in joint work with Abhishek Jain, Zhengzhong Jain, and Giulio Malavolta. End-to-end encryption is now more important than ever. Most of our day-to-day activities happens over the internet, and indeed, like many organizations have taken end-to-end encryption seriously and have incorporated this on their platforms. So the simplest form, end-to-end encryption works like this. Let's say there are a couple of users. Both of them have a shared key that they use to encrypt the messages that they send to each other. And the messages are usually sent through some platform owned by some organization. So now the question is, who generates the key K? Right. So suppose let's say user is using the key to encrypt these messages. Who generates this key? So there are two possibilities we can consider. One is that the organization which is handling the message transmission mechanism itself generates the key, or maybe the user generates the key. Let's consider these two cases separately. The first case is when some organization generates the key. In this case, there are a couple of issues that could occur. So one is data breach. So what could happen is that suppose let's say an organization stores a database of keys of all the users. It could happen that set of hackers hack into the system, and then they steal all the keys in this database. Right? So this compromises the privacy of all the users that are using this particular platform. Another issue that could occur is mass surveillance. So it could happen that law enforcement agencies or government could maybe subpoena an organization to reveal the set of keys that they have stored in their database. And once the organization is sort of forced to reveal the set of keys it has stored, there is no control over how the law enforcement agencies can use the set of user keys. They could perhaps use it to conduct mass surveillance, and we no longer will have any control over what they do. So it seems like there are two major problems associated. The two major problems that occur if we allow the organization to generate the keys. So let's go to the other scenario where the user is the one who generates the key. So here too, there are a couple of major issues. The first major issue is that there won't be any access to the law enforcement, right? So what does this mean? So suppose let's say there's a criminal that the law enforcement agencies have been able to identify. Then they recover a device of this criminal, and they realize that this device contains some encrypted contents. So now if the criminal is the one who generated the key and has maybe destroyed it somehow, then the law enforcement agencies will have no way to recover the underlying data. So potentially this data could contain some sensitive material that the law enforcement agencies could have used to stop further crime, and now they will no longer have access to it, and this is an issue. So the other issue is that this restricts computing on encrypted data. So what does this mean? So suppose let's say the user encrypts his data, denoted here by M, using the key he or she generated, and suppose let's say the ciphertext is stored in some cloud service. So now we often want the cloud service to perform some useful computations on this encrypted data. The cloud service can perform some sort of homomorphic computation on this encrypted data, but the problem is the result is still encrypted, right? And the organization cannot decrypt this because they don't have the decryption key. Of course, you can ask the user to decrypt it, or like you can maybe ask the user to generate some keys for you, but this process involves more overhead, and adds more and it's more cumbersome. So this has sort of led to the encryption debate. On one hand, you have users and privacy advocates, and on the other end, you have the government and the law enforcement agencies. So the users and privacy advocates are fighting to keep end-to-end encryption. They are saying that end-to-end encryption is a necessity. On the other hand, the government and law enforcement agencies have actively called for abolishing end-to-end encryption. So the natural question we ask, in this work is there a middle ground? Can we come up with a solution that can satisfy both these different entities on the different sides of the aisle? And we introduce a notion towards addressing this very, very complex issue. We introduce a notion called pre-constrained encryption. So what is pre-constrained encryption? So in this notion, we say that we go back to the first setting where the organization is the one who generates the key, the decryption key. We're going to call this organization an authority from now on. It generates a decryption key K star. However, this key K star does not have unlimited decryption power. This key K star can only recover a restricted amount of information about the underlying message. So what does it mean for K star to have limited decryption power? Let's look into that using an example. So you can have two ciphertexts. The first ciphertext has some problematic message. It has something that could that might be illegal, right? That might correspond to some illegal activity. For example, it can say something like, let's rob a bank. So in this case, using K star, you should be able to recover the message. On the other hand, you can have a message that is very innocuous. I mean, it's very harmless. For example, we could be saying like, I'm attending ITCS. So in this case, using this key, you should not be able to decrypt the underlying message. So this is kind of the decryption power we want. So we want to be able to decrypt only those messages that might be problematic. All other messages that are innocuous should not be able to decrypt using this key K star. Right. So, and one thing I want to make clear is that we are not trusting the authority here. Even if the authority is malicious, even if the authority generates key K star arbitrarily, meaning that it might not even follow the description of setup algorithm, it can generate key K star however it wants. Even then, we want K star to have limited decryption power. So this is an important property that we need from our notion. So in particular, even if the key K star is generated maliciously, if I have a message saying like I'm attending ITCS, should still not be able to decrypt. So more formally, how do we define this notion of limited decryption power? So we consider a function space. So we consider a function class that is associated with our notion of pre-constrained encryption, and we partition this function class into two categories. One category corresponds to authorized set, the other category corresponds to the unauthorized set, and we require that whatever information you can recover from K star corresponds to this authorized set. So you could have any function in this authorized set. Using K star, you can only recover the output of the function in this set on the message. Okay, so suppose let's say there's a user, there's a key K star associated with it. he encrypts the message M using the public key PK generated by the organization. And now, using K star, you can recover f of M if and only if f is authorized. F belongs to this authorized set. And how do you determine f is authorized? I mean, this depends on K star. So K star essentially determines what are the class of functions that are authorized and what are the class of functions that are not authorized. Okay. So you might ask this question. So it seems like using K star, I can only recover f of M in the case when f is authorized. But what if I want to recover the entire message, right? I mean, in many settings, we do want to make sure that someone can decrypt the ciphertext completely. And how can we ensure using this? So we can fix this problem by introducing another mode. So in addition to this notion that we are using, which is pre-constrained encryption, I can use another normal end-to-end encryption, corresponding to this red key K. So now the user encrypts with respect to both key K star and K, and sends this ciphertext over. And a user that has this key K, the red key, can decrypt the message all the time. So it's not associated with any functions, and as long as it has K, this is like the master key, it can recover the message all the time. So more formally, you have these two modes. In one mode, you can think of the authority being able to recover f of M only if f is authorized using the blue key K star, whereas an end user, another user will be able to recover key K, or recover the message M if it has the red key K all the time. Okay, so this is like an overview of our notion. So we're going to we already said that the authority could even if the authority is malicious, K star should have limited decryption power. So I'll just give you like an overview of what our notion entails too. So we're going to go into the details more formally. So before that, I want to mention one more thing, which is that depending on how K star is defined, you can have two extreme cases. In one extreme case, you can have the set of all functions to be authorized. In this case, the organization or the authority can decrypt everything, right? It can recover f of M for every M, which means that it can recover the entire message M. On the other hand, you can define K stars as that all the functions are unauthorized, in which case the organization or the authority can decrypt nothing. So these are the two extreme cases. Okay. So just to give you some examples of authorized classes of functions, you can have a function that says you output 1 if and only if the input contains some objectionable material. For example, we looked at the message that said let's rob a bank. This contains some objectionable material. In this case, if you have a function that outputs 1, we can also have a function that outputs 1 if and only if the input is a spam email, right? So you're only authorizing functions that classify the input as spam. Any other function that's trying to learn some additional information about the message is classified as unauthorized. So depending on the kind of applications you're looking at, you can define the authorized class of functions. So the first bullet corresponds more to what sort of information law enforcement agencies might need from the encrypted data, and the second bullet point might correspond to what organizations might want to compute on the encrypted data. Okay, so let me get into the formal details. So the notion of pre-constrained encryption consists of many algorithms. The first algorithm is a setup algorithm that takes as input circuit C and outputs two keys. One is SK and another one is PK. SK is the secret key and PK is the public key. Okay. What is C? C corresponds to a constraint circuit. So remember I mentioned that the key sort of classifies sort of partitions the class of functions into two categories. One was the authorized and the unauthorized set, and the classification is done via this constraint circuit C, right? So if C on input of function outputs 1, then it's authorized. If C on input of function outputs 0, then it's unauthorized. So C essentially partitions the class of functions. So and then you have the encryption and the decryption algorithms as in any encryption scheme. So the encryption algorithm is the same, so I'm not going to go over it. So the decryption algorithm, in addition to the decryption key, also takes as input F and CT. And the decryption algorithm outputs f of x if and only if f is an authorized function. In other words, C of f is 1. So this is how decryption is defined. Going back to the earlier example, so the organization produces pk and k star using the setup algorithm. Like k star is sk, and then the user encrypts the message m using the public key, and then you can decrypt using k star and f to get f of m, only if f is authorized. You can consider another scenario where it's not the authority that is doing the decryption and recovering f of m, but instead it's some law enforcement agency. So in this case, how will the agency recover f of m? Right? So one way could be that the authority sort of shares this k star with FBI or like some other law enforcement agency, and then they can recover f of m for any authorized function f. But maybe the authority is not comfortable with sharing this decryption key. In this case, how will the law enforcement agency recover f of m? So what could perhaps be useful is some sort of a key delegation feature where from this k star you can recover a restricted key skf, and then the law enforcement agency can use this restricted key skf to recover f of m. So if pre-constrained encryption had this additional feature, then that would be useful. So we're going to study this additional feature. This is accompanied by an algorithm called keygen algorithm that takes as input the secret key sk and function f and outputs skf. This is it's a sort of a functional key associated with f, and the decryption algorithm now takes as input skf and ct and outputs f of x, as long as f is an authorized function. In other words, c of f is 1. Right? And just to recall, c is the circuit that's input to the setup algorithm. So this is a constraint circuit. Okay, so what are the properties we require? There are 3 properties that we require. One is correctness, which says that should be able to recover f of m as long as f is authorized. So this should be allowed. The other property is that even if the authority is malicious, we should not be able to recover f of m for any unauthorized f. So defining this security notion is somewhat non-trivial and challenging. So I won't have time to go into the details here. I encourage you to look at the discussion in our paper. And finally, we have the constraint hiding property, where we require that the public key pk hides the circuit C. Okay, so there are a few like special cases of pre-constrained encryption that are useful for us. So let's look at these special cases. The first special case is called attribute-based pre-constrained encryption, and the set of functionalities associated with this notion is very similar to the type of functionalities which we have studied in attribute-based encryption. Hence the name attribute-based PCE. So this function every function in this family takes as input x and m. There are it has the input has two parts, and it outputs m if and only if some function g, where this function f is parameterized by g, where this function g outputs 0 on x. And you can also consider the identity-based pre-constrained encryption. So this is again defined analogous to identity-based encryption. So here the function in this function class uh, is every function in this function class is parameterized by some identity id star. It takes as input id and m, and outputs m if and only if id equals id star. Okay, so let's state our results. So we have many results in the paper, so I'm only going to give a snippet of what are the most important results in the talk. So the first result is that we show that PC is as powerful as IO. We show implication from PC to IO, and also the other way around. We also use some additional assumptions in these transformations, which I'm not going to highlight in this talk. I encourage you to look at the paper for the precise assumptions used to go from one to the other. And then we show that you can construct the special cases of pre-constrained encryption, which are the identity-based pre-constrained encryption and attribute-based pre-constrained encryption from the learning with errors assumption. So for identity-based PCE, we get it for all class of uh, identity-based functionalities from learning with errors, whereas for attribute-based PCE, we only get for point constraints. Right, so in the identity-based PCE, there's no restriction on what the constraint circuit can be, what the circuit C can be. In attribute-based PCE, the circuit C has to be a point constraint. So what is a point constraint? A point constraint is associated with some point x star. It's a binary string, and it outputs 1 on all the functions that output 1 on x star, right? So this constraint C takes as input a function f and outputs 1 if and only if f outputs 1 on x star. Okay, so this notion of PC seems very similar to the notion of functional encryption that is fundamental to cryptography. So what are the main differences? I mean, there are two main differences. The first difference is that if you ignore the key delegation feature of pre-constrained encryption, it's still a uh, non-trivial primitive to achieve. Whereas if you take functional encryption and then strip off the key delegation feature, then it coincides with the notion of standard encryption, right? So this is something that we are very, very familiar with. The other difference is that collision resistance is not guaranteed. So what do I mean by this? So suppose, let's say, I give you keys corresponding to functions f1 through fq. So in PC, there is no guarantee that using the outputs of these, or rather using the keys corresponding to f1 through fq, you cannot recover the output of the function fq plus 1 on the input. As long as this function fq plus 1 is authorized, you could obtain the output of fq plus 1 on the input, and the function and then the encryption scheme does not disallow this scenario. Whereas in functional encryption, if you get a bunch of keys, then the only information you essentially can learn are the outputs of the functions associated with these keys and nothing more. Right? So collision resistance is a very, very important part of functional encryption, whereas PC does not guarantee that. So in the paper, we have a little more in-depth discussion on the differences between these two notions. We encourage you to look at it. So in terms of related work, I mean, questioning the trust of questioning whether to trust the authority who generates the setup is not new to our work and has been studied extensively in the crypto literature. It started with the work of Boone and Franklin, who raised the question of constructing encryption systems with multiple authorities. Like there are multiple authorities, each of them produce some keys, and then the security of the overall system is guaranteed as long as we trust a subset of these authorities. So this has been studied in the context of identity-based encryption, attribute-based encryption, and so on. And then we also have the notion of accountable authority. Here, there's authority who we know has maliciously deviated from the protocol. We have like evidence that this authority has cheated. We can hold it accountable, right, to an external judge, right? So that's this notion has also been studied in the context of advanced encryption systems. We also have like registration-based encryption, which is more closely related to identity-based encryption, where there is no like single setup trusted authority who produces the public key. Instead, all the users like produce public keys on their own, and there is sort of like an aggregation feature which aggregates all these different public key into a short public key. So in some sense, it tells us how to get rid of the trusted authority altogether. Okay, so we are going to go into the technical details of our work, and we are only going to focus on attribute-based pre-constrained encryption for point constraints, right? And we are going to show how to construct this from the learning with trust assumption. So the main insight in our construction is the following: we observe that there are there are proofs of advanced encryption systems, specifically like selective security proofs of advanced encryption systems in the cryptography literature, which have a very special structure that we can exploit to construct pre-constrained encryption. Right. So in some sense, we observe that you can turn some proofs with very special structure into constructions, right? And that's our insight. And just to go into this in a bit more detail, uh, a typical way to define selective security is that you have a challenger and adversary. The adversary needs to sort of declare some challenge message at the very beginning of the experiment. For example, you can think of standard encryption, or even like identity-based encryption, attribute-based encryption, and so on. So the adversary is supposed to declare the message in the very beginning, even before the challenger starts giving out the public parameters. Okay. So again, like if you are looking at more advanced encryption systems, like you'll also have these like key query phase which the adversary can do, okay, where the adversary queries a function and the challenger returns back some functional key and so on, right? And this key query phase can happen over many iterations. So typically, you know, the way you prove selective security is, as by a sequence of hybrids, and there is like a very important hybrid which shows up in many selective security proofs. So what is this hybrid? In this hybrid, you have a challenger who produces a fake secret key and a fake public key, such that this fake secret key is such that it cannot even issue keys for inadmissible functions. So what functions are inadmissible? It depends on the specific notion we are considering. For example, the class of inadmissible functions might be different for identity-based encryption, attribute-based encryption, and so on. So in the intermediate hybrids, like there is a point where the challenger produces a fake secret key and a public key, where the secret key does not, even if you have the secret key, you cannot issue keys for these admissible functions. And this sort of hybrid is very useful for um, our notion of pre-constrained encryption. Why? Because I can use this procedure to create the setup algorithm of PC. Right? So the setup algorithm takes as input x star. So recall x star is like the challenge attribute declared by the adversary. So in our setting, x star corresponds to the point constraint. The setup outputs sk fake and pk fake as done by the challenger. So the key generation algorithm can issue keys for any function that is admissible, right? Um, so in our case, we can define admissibility in terms of whether like it's authorized or not, right? So the class of admissible functions corresponds to the class of authorized functions for us. So keygen can issue skf if and only if f is admissible, right? And if it's not admissible, skfa can simply not issue the key. Okay, so with this sort of high-level idea in mind, we will see how to construct pre-constrained encryption for point constraints. And the inspiration for our construction will come from the selectively secure AB construction by Bone, Gentry, Gorbanov, Halevi, Nikolenko, Vaikunthanathan, and Vinayagamurthy. Okay, so what is the setup algorithm of our pre-constrained encryption notion? The setup algorithm takes as input x star and outputs a bunch of matrices. Okay, so you have the matrix A, where matrix A is of dimension n cross m. M is like roughly n log q, where q is the field size. So every entry in this matrix comes from zq, and the number of columns is roughly n log q. This is the matrix A, and then you have a bunch of matrices that encode x star. The first matrix encodes the first bit of x star, the second matrix encodes the second bit of x star, and so on. Right? So the encoding is defined as a r I minus xi star g, where ri is a matrix 0 1 entry matrix sampled uniformly at random. P is an n cross m matrix that is sampled uniformly at random as well, and G is the gadget matrix that is used in many lattice-based constructions. So this is the public key, and the secret key is R1 through RL, and you also have X star. So anyone who is familiar with the proof of security of the AB construction by Bone et al. Will realize that the public key and secret key as stated here is what would be generated by the challenger in the hybrid experiments. Okay, and then we have the encryption algorithm, which is essentially the same as Bone et al. Encryption. So you have the encodings of xi, and then you have the encodings of oh, there's a typo here. This has to be S, not S transpose. So you have encodings of xi, and then you have encoding of the message m, and then you have give out the LW sample. Okay, so how do we generate the key? The key is going to be a short trapdoor. Um, like short just means that the trapdoor contains very small entries, such that if you consider the concatenation of these two matrices A and ARF plus G, where RF is some function associated with F and the matrices R1 through RL, plus G. So if you consider the concatenation of these two matrices, multiply with T, you're going to get 0. We can produce this trapdoor using a procedure called as sampled write procedure. So you're going to use the fact that RF contains small entries, and you know what RF is. Now you're also going to use the fact that you know the trapdoor for G to produce T. So if you're familiar with the Bone et al. Paper, they actually use the sample left procedure to produce the trapdoor. They use the fact that they know the trapdoor for A to produce T. But in our case, we're using like we don't know the trapdoor for A. We're just going to use the fact that we know RF and the trapdoor for G to produce T. Okay. Um, so one thing that we didn't take into consideration is the fact that A could be generated arbitrarily, right? And like for all you know, the authority could generate A with the trapdoor, um, you know, with generate A along with the trapdoor for A. In which case, it can actually generate a key for any function it wants, uh, irrespective of whether this function outputs 0 or 1 on X star. So what we do is we first of all consider the setting where it's semi-malicious, meaning that the authority can pick whatever randomness it wants for setup, but it's still running the setup honestly. In this case, by imposing some structure on A, inspired by the work by Brzezinski and Dortling, we can argue that the the construction still satisfies security. And in the second step, we can go. What we do is we go from semi-malicious to malicious security. This is completely a generic construction. We can start with any semi-malicious AB, and we can compile it to a maliciously secure AB construction. Where malicious here just means that the setup could be maliciously generated. Um, so in this case, you can go from one to the other using secret sharing and also like non-interactive witness indistinguishable proofs. So these are the tools used, but I'm not going to go over how this transformation is done. Right. So this sort of concludes the discussion on how to construct uh, attribute-based PCE for point constraints. So you can okay. So to conclude, we introduce a new notion called pre-constrained encryption, and we gave constructions of this notion from different assumptions. I think this is an exciting notion that has potentially not only other theoretical applications. I mentioned that it implies I/O, so this could be a new pathway to construct I/O, but it also has implications to potentially to aid law enforcement in recovering some information about encrypted data, while at the same time not giving unlimited power to law enforcement. So in that way, this has both theory and potentially applied applications, and there is more work to be done. Thanks.